Hello, everyone, and welcome back to our series on the theory and algorithms of knowledge tracing. Today, we're diving deep into a crucial enhancement of a classic model. We're going to explore BKT with forgetting. If you've ever wondered how to model the simple fact that students forget things over time, you're in the right place. By the end of this video, you'll understand exactly how the forgetting button works step by step. Let's get started. Here's our roadmap for today. We'll start with a simple analogy to get the core concept. Then we'll break down the 5 essential parameters. The heart of the video will be a detailed, step-by-step calculation where we'll watch the forgetting mechanism in action. We'll also discuss how we actually find the forgetting rate in real-world scenarios. Finally, we'll wrap it all up with a clear summary flowchart. Let's begin with the big idea. Let's start with a simple analogy to grasp the core idea. Think of standard BKT as a teacher keeping a list of how well a student knows each topic. This list only changes when the student does a problem. Now, BKT with forgetting is like that same list, but it's written with disappearing ink. If a student doesn't review a topic, their mastery probability automatically decreases over time. For instance, if Xiaoming masters a concept with 80% probability today and then doesn't touch it for 3 days, the model will assume he's probably forgotten some and lower that probability, say, to 65%. This is the forgetting button in action, and it's always active in the background. To model this, we use 5 key parameters. 4 of them are from the original BKT model: the initial mastery level, the learning rate, the guess rate, and the slip rate. These represent the student's starting point, their ability to learn from practice, their chance of guessing correctly, and their chance of slipping up. The star of the show in BKT with forgetting is the 5th parameter, delta symbol, the forgetting rate. This value dictates how quickly the student's mastery decays over time when they don't practice. This is the key difference that makes the model so much more realistic. So, how does the model work its magic after each question? It follows a specific 3-step process. The most important thing to remember is the order. First, if any time has passed since the student's last attempt on this topic, we apply the forgetting update. We decay their mastery probability to simulate real-world memory decay. Only then do we proceed with the standard 2 steps: the observation update, where we adjust the probability based on whether they got the question right or wrong, and finally, the learning update, where we account for the new knowledge they gained from the attempt. This order is critical. Forgetting is always the first step, which is a key improvement over the original BKT model. There are a few ways to calculate forgetting, but the most popular and theoretically sound method is exponential decay. This formula closely resembles the classic Ebbinghaus forgetting curve, which describes how human memory fades. The formula is L forgotten equals L old multiplied by e to the power of negative delta multiplied by delta t. Here, L old is the mastery probability before the time gap. Delta is our forgetting rate, and delta t is the time that has passed. The e is a mathematical constant. The key takeaway is that forgetting happens quickly at first and then slows down, which aligns perfectly with how our own memories work. This is why spaced repetition algorithms, like the ones used in apps like Anki or Duolingo, schedule reviews more frequently for recently learned items. All right, let's roll up our sleeves and see this in action with a concrete example. We'll follow Xiaoming as he learns linear equations. Here are our parameters. He starts with a 30% chance of knowing it, learns at a 20% rate per attempt, has a 10% chance to guess correctly, a 15% chance to slip up, and crucially, his knowledge decays at a rate of 5% per day. We'll track his progress over 5 days with 2 attempts and a gap of 3 days before his 3rd attempt. On day 1, Xiaoming attempts the first question and gets it wrong. We start with the observation update. Using the formula for an incorrect answer, we calculate the new probability. Plugging in the numbers, we find the probability that he still doesn't know it is about 93.3%. Therefore, his mastery probability drops significantly to just 6.7%. Since he got it wrong, there's no learning update, and since it's the same day, no forgetting occurs. So, at the end of day 1, his mastery is at 6.7%. Now, day 2. This is where the magic happens. Xiaoming gets the second question right, but before we process that answer, we must apply the forgetting update. 1 day has passed, so we use our exponential decay formula. His mastery drops slightly from 6.7% to about 6.37%. Now we can process the correct answer. Using the observation update formula, his mastery jumps to 36.6%. Finally, we apply the learning update because he got it right, increasing his mastery to 49.3%. Notice how forgetting was the very first step. Let's jump to day 5. Xiaoming hasn't practiced for 3 days. Just before he attempts his third question, we apply the forgetting update again. This time, 3 days have passed. Using the formula, his mastery of 49.3% from day 2 decays to approximately 42.4%. That's a drop of almost 7 percentage points over 3 days. This is the tangible effect of the forgetting mechanism we've been discussing. It shows that knowledge isn't static. It fades if not reinforced. You might be wondering, how do we get the value for delta symbol, in the first place? There are 3 main methods. The most common is to calculate it from historical data. We look at how students' performance on a topic drops off over time and use that to find the best fit decay rate. Second, we can use values from cognitive science as a starting point. Third, in more advanced systems, we can even create a personalized delta for each student, acknowledging that everyone's memory works a bit differently. To wrap everything up, here's a flowchart that visualizes the entire process of BKT with forgetting. Starting with the current mastery level, the first check is always, has time passed? If yes, apply the forgetting update. Then, based on whether the student answered correctly or incorrectly, we apply the corresponding observation update. If they answered correctly, we also apply the learning update. Finally, we have the new, updated mastery probability, and the cycle repeats for the next question. This loop is what makes the model dynamic and responsive to both practice and the passage of time. So, to recap, BKT with forgetting is a powerful upgrade because it accounts for the simple fact that we forget things over time. The key step is applying the forgetting update first. This makes the model much more realistic. Looking ahead, the real power of this model comes when we use it to intervene. By knowing exactly when a student is about to forget a concept, we can use reinforcement learning to schedule the perfect review question at the perfect time. This moves us from just predicting student performance to actively shaping it. And as recent research suggests, models like this are also important for green AI. They provide excellent insights without the massive computational cost of some newer, more complex models. Thank you for watching, and stay tuned for our next video in the series. That's all for today's deep dive into BKT with forgetting. I hope this step-by-step guide has demystified the process for you. If you have any questions, please leave them in the comments below. Don't forget to like and subscribe for more content on educational data mining and learning technologies. Thanks for watching, and I'll see you in the next video.